All right, well, we're back again. We're just taking a look at some of these other problems. So we went through a whole bunch of stuff with whether we use ice or the Henderson-Hasselbalch, and now we're going to kind of deal a little bit with it again. But look at number 18. It asks here, what is the approximate concentration of the NaOH sample? This, when you're taking a look at titration graphs, this is the exact same thing that we've looked at, but it's just kind of flipped. This starts off with a base, and then they're adding acid. And so the equivalence point, that still works the same way that we usually do. The pK, though, just to let you know that if you're looking at a graph like this, halfway would be considered the pKb for that base, not the pKa. So just to clarify. And but when you're at this equivalence point, it's the same thing that we had before. It's like moles of our thing that we adding in, like here we're adding acid. It equals the moles of the thing that we started with initially. So moles of acid added equals moles of base initially. You can calculate what those are based off of the concentration of the HCl and the volume of the HCl that they gave you. That's kind of what all these calculations are for, is molarity equals moles over liters. Solve for the moles of the HCl, that's equal to the moles of NaOH that were there initially. Solve for the molarity of the NaOH, because it has to be divided by the liters of the NaOH that you started with. Yeah, that's kind of what it is. This is one thing that you have to be able to do. And so, yeah, we're good there. But then, getting into some of the other problems that involved work. Things like number 22, again, they gave you some information, and when they say that you have a buffer, nice, you can use Henderson-Hasselbalch. And then you can skip the ice problem. So here you're just kind of considering what those concentrations should be in order to get this pH. This concentration of A minus has to be larger, and the concentration of HA has to be smaller. And so in order to make this equation work out the way it should, and this number needs to be greater than 1. But you can also reason that, well, if it's more basic, you have more of the base part in there, and then less of the acid part in there, or the conjugate acid, and more of the conjugate base. Okay. So, anywho, so let me clarify 25 here really quick. 25, there's a lot that's written on here, and it does deal with Henderson-Hasselbalch. You're only dealing with this first one, though, because Henderson-Hasselbalch, it's pKa. You can just use that. This one gives you a Kb. You can go through and figure out what that is, but this is just a whole lot easier. But when we work through this, and they tell us that we have 100 milliliters of this one, or sorry, 0.1 molar of our conjugate acid, our conjugate base, and then they add some NaOH to it. You can kind of work through the problem, or just think through the problem that we're adding a strong base, and a buffer does not change the pH significantly. It works in that buffer zone on the pH, or on a titration graph. So the pH does not change very much. The thing about 25 is that they don't tell you how much of this stuff that you started with, so you don't know if you're if this stuff is your limiting reactant or not. So you just kind of assume that you have enough. And you're just telling what is adding the strong base, how does that affect the pH? It doesn't change it that much in a buffer. That's kind of nice. And but then 27, this part, you had to write out your net ionic equation. Even though they gave you this ionic equation, they are telling you that it reacts with NaOH. So that's okay to write out your own net ionic equation as long as it makes sense for what's being added. And so if you need to do that, you can do that. And then because it involves a strong base, you have to set up the BCA table. And it needs to be in moles. So you have to figure out moles of your CH3COOH from this information that they gave you. Put that into the before piece, the OH minus. They told you how many moles of NaOH that you added. And the Na, it's going to be a spectator ion, so you don't include it in here. And then because you have 0.3 moles here and 0.1 moles here, the OH minus is your limiting reactant. Set up your change, minus X plus X. And over here, because this is our limiting reactant, we're going to have 0 left over. And then we're going to have 0.3 minus X. And then X, we can figure out what X is simply from this. It's equal to 0.1. Solve for how many moles of each substance that we have. And we're back to being at a buffer. And where we have the conjugates, the conjugate acid, conjugate base. We put those into the Henderson-Hasselbalch equation. And you can use moles, and then the pKa, they gave it to you, nice, and then we solve for the pH. So that's kind of how you go about doing that one. And again, Henderson-Hasselbalch is a very nice shortcut how to do this. But in this one, when they're telling you this thing that happened and where solution was mislabeled, and you can use this as kind of a way of telling what's going to happen. You had this 1 molar solution rather than 0.1 molar. So the 1 molar solution is what you need to use in order to figure out how many moles of OH minus that you have. Start off with that net ionic equation. You have to do this BCA table. You have to have moles. Figure out how many moles of each substance that you have. You just have to use this 1 mole or 1 molar for the concentration because that's what it actually is. And then you really have 0.5 moles here. That means that out of the 2 of these, this, our weak acid, is our limiting. And we start off with 0 over here. Sorry, I forgot to label that. You have your minus X plus X. And then because this is our limiting, we get 0 for the after part. For OH minus, we have 0.5 minus X and X. And then we can solve for what that X is from just this relationship. But the key here is that, yeah, you have this conjugate base here, but you have a significant amount of OH minus left over, which means that the base took over the buffer. And instead of staying in this buffer zone on like a titration graph, it ended up overtaking the buffer. And now it's like being in this region where it's all basic because the pH is now ruled by how much OH minus ion is there. And because that came from a strong base, this is predominantly what the concentration of OH minus will be. And so that's a little bit with number 29. And then your last one, 30, they kind of talk through this, and this was kind of a weird, like there was a mistake in lab and you're explaining it. But feel free to ask questions, and I'll make sure I have the annotations for the FRQ up as well. So you guys are doing awesome. Feel free to ask questions, but yeah, we'll kind of wrap things up on Tuesday. So have a wonderful day.